Hello everyone, and welcome to this webinar with the Danish Sound Cluster. And my name is Pedro, and I'm here to moderate this event. You probably remember me from the last one, so I'm here for a few more. And today we have two guests with us, Martin Krume and Eric Behind. And I'll give you a short introduction of who they are, but before that, I will tell you a little bit about what we're going to talk about today. It's called Beyond DSP, and actually it's a multi-series or multi-episode series. And the first episode is about this special architecture that Greenwave started exploring, an academic to begin with, discovery, and then applied in the professional world. And then, Martin is going to talk a lot about this technology and also how they managed to match that with other technologies to have something beyond DSP. And then Eric will come afterwards and talk about a more use case scenario where you have on the product side, and you will be presented with a more use case scenario. So just to give a little intro, Martin is the VP of Marketing at Greenwave Technologies. He's not going to do any marketing today. He actually has very in-depth knowledge within the technical fields. So Martin is going to tell you more about it, what he's going to talk about. And then Eric is the CTO of Orosound. And Eric is an entrepreneur, and he's also done his patents. He has contributed a lot to the field of audio and AI and combination of those two. And he works with the headphones that he's actually wearing. So I won't say much more. I think you guys will be much better at talking about yourselves. So let's start with Martin. So Martin, the stage is yours. You can start sharing.
Okay. Thank you very much. Thank you very much, Pedro. I'm just going to go ahead and share my screen.
Awesome.
I think you should see my slides now.
Yes, we do.
Great. So thank you very much for the introduction. Yeah, as Pedro said, we're going to kind of take two parts to this. The first part that I'm going to look at is kind of, we think of as sort of kind of bottoms up. So it'll be more looking at the processor architecture, why we came up with it, what it does, what are the tools, how do you use it, what are the kind of things that you can run on it, and so on. But looking from the bottom up, and then we'll look from the top down. So we'll look from the application, from the audio application perspective down, from the audio algorithm down. You know, how do you use this? Why is it good? Why is it interesting? What can you do with it that's different to what you could do before? So I'm going to give a little introduction on who Greenwaves is, so you're all aware of who we are, and then I'll get gradually more technically deep into the processor architecture. If there are any questions, there's a Q&A button in Zoom that's at the bottom. So if you just start, putting those questions in as soon as you have them, and then I'll answer them at the end of my session. And I think we'll do another question and answer session at the end of Eric's session. And then we can do a kind of final kind of combined questions and answer session at the end of both sessions, or some kind of discussion or anything of that sort that comes out of the overall presentation. So let's start off on who's Greenwave Technologies. Greenwave Technologies business is making chips. We're a fabless semiconductor, which means that essentially we design the chips and then they're made by a production company. And really our focus is on processors and processors that are capable of very extreme levels of performance in very, very energy constrained devices. So we work in devices like, hearables, where the battery is super small and has to last for, a day or something of that sort. We also work in products where the batteries are bigger, but the product has to last for years. We have 40 people, mostly in Grenoble in France, but we also have offices in Bologna in Italy and Shanghai in China. The Bologna office is actually right next to the University of Bologna. And we have a very tight research relationship with University of Bologna and ETH Zurich, who jointly have a program that they call PULP, which stands for Parallel Ultra Low Power. And that's a research project that has, I think, been around for about 12 years now, and is really concerned with extracting power efficiency out of using parallelism. Parallelism means, running things in parallel. And that's a basis and a kind of research side of what we do. Our first product was called GAP8. It's been in production since 2020. It was really focused more on the IoT sensor area. So devices with slightly larger batteries, but that have to last for years. And GAP9 is the product that I'll be talking a lot about today, which is more focused on audio. However, does extend to what GAP8 was capable of doing. And it's been in-house and sampling to customers since Q2 of 2022. So really, I mean, GAP9 and some of the things that GAP9 does really comes out of some ideas of what are going to be the next generation of audio experiences, and what kind of constraints does that put on hardware. And I just took two here, and I didn't, because I could go on about lots of different audio experiences, but this is just two to give you an idea and to kind of drill down on what makes them different. So one of the things which is very recent is the idea of adaptive transparency. So transparency mode has been around for a long time. It's the idea of letting in some sounds through something that's blocking your ear, letting those sounds in, and when you're in the street, so there's an ambulance coming or someone horns or whatever, you want to be able to hear those sounds even if you're listening to music, so that you can know that you might get run over. So what do we need to do that? Well, the classic side has been to let in a certain amount of the external sound. Now we're starting to get algorithms which are allowing you to identify these kind of non-static sounds, because a horn is not something that's happening all the time. These non-static sounds that are outside, and create a filter which lets those through into your ear. And so if you're going to do that, what do you need? Well, first you need to have quite a sophisticated and fast thing that's going to spot this filter that needs to be constructed to let this external sound in. And generally, people are more and more looking towards the regression capabilities of neural networks to do those kind of algorithms. And then secondly, what you're going to need is some kind of filter path that you can kind of configure so you can let this sound in. And you're going to need that to be quite low latency, because you really don't want to have a long lag between the sound that's happening, or this event that's happening, and the ability to configure this filter to actually take the sound in. So ultra low latency kind of time domain filter path combined with kind of a low latency, high load neural network type processor load. Look at another thing, which is call speech denoising. This is something that's been happening mostly in the cloud up until now. There's a number of companies that do this. There's also a lot of the companies like Zoom that do this kind of denoising in the cloud. So this is essentially taking a noisy speech signal, so a speech signal that's mixed with noise, identifying the noise in that signal, and then cleaning that out of the signal. And again, this is being handled, is handled in a modern sense by neural networks that are essentially identifying that noisy segment of the speech, or can be handled by those. And there's a number of different companies that are proposing solutions which are happening in the cloud. That there's a desire to bring that down to these kind of devices, so very, very energy constrained devices. Why? Well, because you want to preserve privacy. You don't want to send all of these signals into the cloud and then back again. You want to reduce load on cloud systems. You want to reduce energy used transmitting all of that stuff. Again, what do you need? Well, you need low latency, high load neural network processing that's inside a very low energy device. There are some extra issues that come into this. Obviously, the energy issue. So in all of these cases, you've got to be doing this with a low level of energy. And the second issue, which is also just as important, is development time. You need to be able to get some of these things into a processor platform in a way that's not too difficult or complicated to develop. And so these are kind of some of the things that we saw that when we were designing GAP9 that affected in the way that we designed the product. So what distinguishes these kind of loads from other kind of processing loads? Well, generally in the audio world, everything's streamed, right? We're handling streams, probably not necessarily synchronized streams, not necessarily streams which have the same clock. Maybe there's clocks that are coming from external or internal to the device, but they're basically streams of samples that we're processing. And this actually is quite similar to what we see in the image world. Again, we're handling streams of quite known size of thing that we're trying to process. They're real time, so latency becomes a real issue. We have to process them in a certain amount of time. And finally, obviously, we're in portable type devices, so they're very, very energy constrained. And classically, this kind of processing has been handled by a special type of processor that we call a digital signal processor. And there's a few things which kind of, identify something as a DSP or been used very heavily in DSPs. And one specific thing is a form of parallelism. So why is parallelism interesting in processors? Why are we using parallelism? Well, one of the things that parallelism allows you to do is essentially do several things at the same time. And that gives you a speed up, hopefully, in what you're doing. So if you do, the same task several times at the same moment, then hopefully you're doing it sped up by the number of times you do it. When you do that, that means that essentially you can reduce the frequency in which you are doing those things. And generally that allows you to design chips which operate at a lower frequency. Once you design a chip that operates at a lower frequency, you can run it at a lower voltage. That already gains you a quadratic benefit in terms of energy. But also, when you design chips that run slower, you can choose transistors that run slower, and they tend to be less leaky and cause less energy to be used by the device that you're designing. So overall, running things slower generally uses less power. And so we try and get things to run slower by doing multiple things at the same time inside the architectures. So the very long instruction word approach to this is to actually build an instruction that does multiple things at the same time explicitly. So you say, I'm going to do an add, I'm going to do a multiply, I'm going to do a load from here, I'm going to do a store from there, I'm going to do a float op from here, I'm going to do a float op from there. Now, one of the challenges with that's going to be one long instruction that you feed at your processor one go, and the processor will have to execute that, or will execute that all at the same time. And essentially what you're doing is you're pushing the job of figuring out, okay, what are those things up to the compiler, which is the thing that's going to take what the programmer has written and convert that into the instructions that the computer will understand. And sometimes actually, because the compiler is not actually capable of really figuring out what these things are, and this is a very long, an old problem with very long instruction word compilers, the programmer is going to have to get involved. So generally, these kind of architectures tend to require programmers that are extremely experienced, very skilled. It tends to be long to optimize. So you tend to have to work a long time to try and pack everything into these very long instruction words, so you get an efficient execution. Because if you don't fill one of these slots, then that portion of your computer is just not working. So it goes dark. Generally, also, these very long instruction word architectures are proprietary. So each company has their own DSP architecture. There are some, DSP architectures which are sold as intellectual properties that get inserted into multiple different chips. So multiple different chips have the same architecture, but generally they're proprietary. So they're difficult to program, long to optimize, and very difficult to change. once you've actually developed your architecture, developed your algorithm in one, you don't really want to move it to another. So given these two things of, the existing world in terms of an architecture and these new demands in terms of very high workloads plus low latency workloads, plus this need to be able to program these things in an easy and efficient way, we kind of came up with this new architecture, this new device, which we call GAP9. So this, at the very top level, looking at GAP9, you can kind of split it up into 5 different things. So 3 things which are to do with the task that it's doing, and 2 things which are kind of horizontal in terms of how it does those tasks. So at the top level, it's a combination of an ability to do real-time, streamed, autonomous time domain digital signal processing. So what is this? This is sample by sample, extremely low latency digital signal processing. And I'll go into exactly how this thing that we call a smart filtering unit is handling this. The second thing is general digital signal processing. So things like FFTs or codecs or things of those sorts. And here we handle these in a programmable, fully programmable RISC-V based, and I'll go into a little bit on RISC-V cluster, so a compute cluster. So this is a programmable compute cluster, programmable in C, and I'll talk a little bit about the structure of this. Then you've got neural network processing. So how do we handle that? Well, we handle that in a combination unit. The cluster also contains a neural network accelerator. So we use both of these things to handle that workload. We combine an ability to be flexible in the sense of having a programmable cluster, and then using NE16, which is a neural network accelerator, to handle the extremely heavy load tasks. And the heavy load tasks in neural networks are generally the filter layers, things like convolutions, linear layers, and the linear layers inside recurrent layers, the matrix multiplications inside transformers, and so on and so forth. Finally, 2 kind of horizontal things. As we said, we're dealing with energy constrained devices. So all of this is operating extremely low power. And then highly flexible, much easier to program versus alternatives. So in a sense, try and make this thing so that you don't have to spend too much time optimizing. I don't think there's any embedded processor that's easy to program. So I always put easy to program versus alternatives because these are devices that require skilled programmers, and really focused in towards hearables and wearables, and that's GAP9. So you can see the product here. It's in a small WLCSP package, and as I said, it's already shipping to customers. I'm now going to go down a kind of a further level and look at really, in an architectural sense, how does GAP9 look? So GAP9 kind of, you can split it into 2 bits. On the left-hand side, there's a structure which looks a lot like a microcontroller. We've got a core, which we traditionally called a fabric controller. This really comes from a historical sense. This is a RISC-V based core. So RISC-V is a new instruction architecture. You can think of instruction set architecture. You can think of it at the same level as, say, an Intel x86 or the ARM instruction set. These are essentially the fundamental instructions that you give to the computer, the encoding of those instructions and so on. And they're things like, add, subtract, move from memory, move back to memory, and so on. This is a RISC-based instruction set. So it means that these instructions are very simple, very elementary, because RISC stands for reduced instruction set. So we're going down to some elementary instructions. Nice thing about RISC-V is it's an instruction set architecture that's open source, that has a foundation that's behind it with a huge amount of support worldwide in it. Its second nice thing is that it allows the extension of it, standard extra instructions to be added to the instruction set. And we've extended this RISC-V core with things like DSP instructions, so things like max, saturation and clipping operations, hardware loops, and so on. Each core has a lightweight vector engine in it, so we can handle 8-bit and 16-bit vector operations, variety of them. Each core also has a bit manipulation unit in it, so we can do things like population counts, bit extractions, bit shuffles, and so on, which are very useful for certain algorithms. And then finally, in GAP9, each core has access to what we call a transpositional floating point unit. This is a floating point unit that allows us to do operations in IEEE 32-bit floats, but also on IEEE 16-bit floats and on B-float 16-bit floats. So for those who you don't know this, IEEE 32 and IEEE 16-bit floats, I think, are known. B-floats are essentially, B-float 16 is something which was brought in at the beginning, I think, by Google. And basically, it's a float that has the same size of exponent as a float 32, so the same range, more or less, as a float 32, but has much less precision. And this turns out to be quite interesting to use in certain types of network, and particularly for on-device training. This core structure is replicated across all of the device. So all of the cores look the same. Why is this interesting? Well, if all of the cores look the same and the memory map of all of the cores is the same, you can write a function in C and it will run anywhere on the chip. This makes it much easier to program the chip, because if you write a function, you don't have to use different compilers to run different things in different parts of the chip. You can write a function, it will run anywhere in the chip. The only difference will be the performance that it sees to memory. So the different memory areas will have a different performance depending on where you run it. Then on the left-hand side, there's some memory. There's quite a large amount of memory. In fact, EMRAM, it's not flash, it's a flash equivalent, so it's a non-volatile memory of 2 megabytes, 1.5 megabytes of RAM, and then a peripheral controller, which is quite a sophisticated peripheral controller that allows us to offload a lot of the work that normally the fabric controller would have to do onto this peripheral controller. We call this peripheral controller a micro DMA, because it's kind of like almost a programmable DMA device. The programmable DMA device also has the ability to actually transform information on the fly. And one of the elements that can do that is what we call the smart filtering unit. So this is a unit which is kind of directly bound towards the interface that you can see on the outside, and can actually process information coming from an interface and send it straight back out to another interface. Okay. It also can process towards the memory, away from the memory to an interface, or memory to memory in blocks. And I'll come to more details on the SFU in a further slide. In terms of interfaces, we have camera interfaces here, but I think from this audience's perspective, the interesting one is the serial audio interface. There we have 3 serial audio interfaces with up to 16 TDM channels per audio interface. So these are I2S interfaces, and that allows us to actually process up to 48 in or outgoing PCM channels. There are also PDM interfaces on each one of these SAI interfaces shared on the pins, and there's 3 PDM in, 1 PDM out on each one of those interfaces. So up to 9 PDM sources in, 3 PDM sources out. And all of the power supply management, things like that, so controlling the core power, is actually managed inside the chip. Why is that important? Well, what we're trying to do is allow someone to actually tune the performance of the chip dynamically to the workload that they need to do. And I'll explain a little bit more when I get to the cluster side, how we do that. So on the right-hand side is what we call the cluster. So this is actually 9 cores. 1 master core, which is kind of like an orchestrator, and then 8 cores, which actually are kind of like worker cores, even though structurally they're pretty much identical. And they are all synchronized through a hardware synchronization mechanism and see shared memory. So they all see exactly the same memory connected through something which we call a logarithmic interconnect. Why is this synchronization element important? Well, essentially what we do is we spin off tasks onto this cluster, which you can think of as like a calculation engine. And essentially these tasks go off onto these cores, which are free running. So each one has its own program counter and can be doing whatever you want it to be doing and programmed in C. But the fork out onto those cores, things like forks, joins, mutexes, semaphores, barriers, all of these synchronization primitives are actually handled through hardware, which means that we can very quickly fork onto all of these cores. when something finishes on a core, so a specific core finishes, but the others haven't maybe, then it can use a barrier, for example, to resynchronize itself with the other cores. At that point, one cycle after it's called the barrier, it's clock gated. So it's no longer consuming power except leakage. And then when all of the cores hit that barrier, one cycle later, they're all woken up again. That's significant in the sense that we can parallelize algorithms and extract speed up from algorithms that have perhaps more difficult parallelization strategies. We can even, in certain circumstances, take algorithms which really aren't parallelizable and then schedule them across the cores and synchronize across the cores and create a pipeline, which again gives us a parallelization capability again. All of these cores, as I said, are identical to the fabric controller, and then we combine into that cluster this NE16 cooperative AI accelerator. So the AI accelerator really takes care of things like convolutions, pointwise convolutions, to a certain extent depthwise convolutions, matrix multiplications, linear layers, and things of that sort. And then we can get the two to work together. So if we have a complicated and in the audio world, we find quite a lot of complicated recurrent structures where there's complicated activation functions that we need to handle. These can be handled inside the parallel cluster extremely efficiently, already extremely efficiently. And then when we want to get the absolute top energy performance, we use the AI accelerator. So all of this structured together is kind of highly parallel, domain-based. So all of these different domains, there's actually 3 different clock domains in this: the cluster, the FC, and the SFU. Which means that we can individually tune the frequency of each one of those to the frequency we want for the particular workload that's happening dynamically. And then there's an overall chip voltage domain, and these are also switchable voltage domains. So we can switch the cluster off when we're not using it completely, and then it's not using any power. All of the data that flows across this architecture, it flows through DMAs. We don't have any data caching in this architecture. So we actually do explicit movements of data across it. That means that, for example, say we have kind of a streamed workload, we actually generate the code to move that streamed workload across the hierarchy of memory there, be it external memory, internal RAM, or shared or L1 memory inside the cluster. And we have some very sophisticated software tools that can do that for us. So what's this SFU? I'm not going to go into the depths of the SFU, but I'll give a little bit of an idea of what it is. So when we hit something like, for example, noise cancellation, we start getting into a domain of latency requirement, which is not really solvable with a classic processor architecture. Just having the problem of having to load instructions, it already creates problems. Having anything which is shared with any other contending resource means that you get determinism problems, which mean that you just can't use this kind of classic structures. So when we saw that, we came up with quite a new type of structure, but we did want that structure to be integratable into something where it was very configurable and could be configured by elements outside it. And so we came up with this thing that we call a smart filtering unit. So it's really focused on sample by sample, stream-based autonomous time domain filtering, which means you get a sample in from, say, an interface like a PDM, you decode it, so you do a sigma delta conversion, you've got a PCM sample, and you immediately start filtering that, and you produce an output and send it out without anything happening, without anything else having to be involved, completely deterministic. It's made up of a number of different highly configurable hardware blocks, including something that we call a global filtering unit that has 13 different filter patterns in it. That can be, and these blocks can be kind of combined to form a data flow graph. And in fact, we can run multiple graphs on this device to the limit of its resources, stop and start them dynamically, and actually update the parameters of them dynamically from outside the GFU without stopping the graph. So why do you want to do this? Well, I mentioned latency. You need to have a low latency if you want to have a structural latency on a 768 kilohertz audio signal, then you need to be able to process samples in 1.3 microseconds. And that's what this is capable of doing. Secondly, power. Everything to do with loading instructions and so on and so forth is consuming power. And it's clear that if you want to get the lowest possible power consumption, you have to produce something that's more or less dedicated hardware. And this is more or less dedicated hardware, but very, very, very flexible in terms of its configuration. Finally, fully deterministic execution time. Again, this is a device that is clocked separately from the rest of the chip, that can be in a state where it does not need to depend on anything else happening in the chip. So it won't be stalled by anything else. It will literally wait for that sample to come in, process it, send it out. Where can it be used? ANC, heavy-duty filtering, sound spatialization, sound effects, transparency, all of these things. And I think we've just started exploring it, and I think we'll go further in finding new things that we can do with it. So how is this combination different to a classic DSP? If we go back to the classic DSP with, say 8, I'm just picking a number, 8 scheduled parallel instructions. So you've got a DSP with a long instruction word, and you have to fill these 8 instruction words. Well, in the cluster, what we have is actually 8 synchronized but free running cores. So we just run a bit of program on each of these. And this could be a way, the classic kind of way of dividing up a problem is to divide the data up or pipeline the problem, or do a mixture of both. So here we could be dividing up the problem. So we're doing the same problem. And maybe we're adding 1 to a load of numbers. So we divide the numbers up into groups of numbers, and we add one group of numbers on each core, and then the final point we synchronize together and say, okay, we're done. It's a very simple example. The difference with here is that we don't actually need to schedule those instructions at the same time. And that becomes really interesting when you start to deal with memory. Because if you're reading in any way from the same kind of memory area, then you start to get contention between these different cores. So a classic approach is then to give them local memory, but that makes them a lot more difficult to program, because you've got to think about bringing things local to the core and then exporting out the results. So what we do is we have this logarithmic interconnect, which you saw on the other slide, and that actually has a tendency to naturally desynchronize the cores so that we get very low memory contention and very great scheduling of all of these instructions at the same time. And well, the proof of the pudding is in the eating. So how does that, how does that perform? Well, we've done some testing, particularly on LC3 codecs, and we've looked at this versus a kind of classic DSP architecture, and we find that we use kind of 2 times less cycles, 3 times less power per operation. So we get an overall 6 times less energy versus this kind of approach. Now, that's a kind of unfair example, because we're not comparing exactly apples to apples in terms of frequency and clock and so on and so forth, but it gives you an idea of the kind of speed up that you can get. Then what we do is we combine that in with heterogeneous portions of hardware, which are configurable blocks like the NE16, which give us, a kind of 80-20 rule energy reduction, and further combine that in with the smart filtering unit, which again allows us to use this cluster to update processing units that are organized in a somewhat different way for time domain signal processing. And it's this combination of parallelization, synchronized free running cores with configurable hardware blocks that gives a completely new type of structure, highly efficient for these kind of applications. A big question always comes is, well, so how do you program this thing? Because great, okay, it's a nice piece of hardware, but it's like a brick if you can't have good tools for it. So we have a number of tools. We first obviously leverage the RISC-V infrastructure. So that RISC-V is, now got 300 or 400 serious companies that are really working on it. And that's generating a lot of interest around tools. So there's things like, GCC compilers, LLVM compilers, and so on and so forth. So we have all of that. But how do we cope with, say, for example, neural networks, getting neural networks onto this thing? We have a whole flow that takes us from things like TensorFlow Lite and ONNX, which are, I mean, the big packages that are used these days to develop neural networks tend to be TensorFlow and PyTorch. This is the symbol for PyTorch. So TensorFlow is a Google thing, PyTorch is a Facebook thing, and also there's a certain amount of development that's done in MATLAB for neural networks. All of these packages, essentially TensorFlow kind of spits out an intermediary form, which is called TensorFlow Lite, which is kind of an exchange format, a way to express an inference model outside TensorFlow. All of the other packages really are concentrating around something called ONNX, which is kind of an open interchange format for neural networks. What we do is we take these formats in and we then produce in a kind of staged approach. We lower that down to C. So we take that graph and we reduce it down to a mixture of generated C and handwritten C. And we feed that into a tool that we call an autotiler. And this is the tool that really determines how we're going to move things around the chip architecture between the external memory, internal memory segments, and make sure that as much as possible, we hide all of that memory movement behind the execution of the actual flow, and make sure that things are in the cluster when we need to use them and out when we finish with them. And that flow is capable of producing things which are optimized for mixed IEEE 16, bfloat 16, 16-bit, fixed point, 8-bit fixed point, and down to sub-byte quantization levels. Then we have an equivalent set of tools really for constructing audio graphs, constructing and then running audio graphs with strong links into MATLAB so that you can construct filters with nice GUIs and so on and so forth for the SFU. And all of the SFU filters can be run in the SFU, but you can run elements of those filters outside the SFU in the FC or in the cluster, and a full runtime for that. And finally, we combine around that. Obviously, I mentioned GCC, but also classic things like a programming bridge, a full simulator of the SOC, a quite complete profiler which allows you to kind of debug stuff, and then combine that with the neural network and the audio graph tools. I'm kind of hurrying up because I'm sensing that I'm going over time. And then we have a full set of boards that you can try all of that out on. And I'll end there and take any questions that you have.
Perfect. Thank you, Martin. We already have two
So I have a couple of
questions.
questions. What is your view on how a neural network needs to be trained to recognize non-static sounds that should be allowed through? Would training vectors be updated regularly in the field as a sort of firmware update? No, they wouldn't be updated in the field as a sort of firmware update unless you make an overall improvement to your neural network. And it is a good question because in this particular case, neural networks create a firmware update issue. Although this is somewhat lighter in the case of hearables, because there's generally ways that we can get firmware to hearables which are easier than sensors that may be halfway up a light pole. But this is actually a very good question in terms of that. The way that the network, those kind of networks are trained is they're trained to actually differentiate lots of different types of noise sources. And this comes to one of the key problems with doing neural networks, which generally is data. We need a lot of different sound samples of different types to train these things. Greenwave doesn't actually handle that ourselves, but partners like Orasound do, and Eric will be talking about that and about what his company does. So that's that. So the answer is yes, one can imagine situations where the networks will be updated, but they're not being updated dynamically for different noise sources. Could you elaborate on the kind of development tools you deliver for this IC? Multi-core debugging, dedicated compiler for each processor, block drivers, example applications, etc. So firstly, there isn't a dedicated compiler for each processor because each processor is identical. So there's one compiler for the whole chip. And obviously there is a compiler, and it's GCC based. It's GCC binutils, classic kind of development environment for that for these kind of products. Multi-core debugging, yes, we support a GDB over an OCD bridge, and we can debug on the device. You can also actually debug the simulator, which often is more easy. The simulator runs on your workstation. It's cycle accurate to 10% error rate, so it will be 90% of the performance of the real chip, and gives you really great visibility on what's actually happening inside your code. So you can do things like hotspot identification and so on. But yes, you can debug multi-core code with that. Block drivers, there are drivers for all of the peripherals on the and BSPs for different boards that we have, and the ability to generate new BSPs, and a number of drivers for external peripherals and so on. There's a load of example applications which go from kind of individual examples of how do you do this, how do you do that for each device, and for general things like how do you spin off a task onto the cluster, how do you create a file system, how do you do all of those kind of things. Then we have something called NN menu, that is a kind of menu of different blocks that you can kind of put together, and we're adding audio things into that NN menu. So it goes everything from simple things like specific neural networks that we've ported across, so well-known neural network structures, up through kind of combinations of those neural network structures to fully applications. So a combination of neural network structures with a bit more pith around it could be something like noise reduction. So, and we do actually include an open source noise reduction example. Now, we're not saying that it's ready for production. It's actually quite impressive. It works very well, but I'm absolutely certain that there's corner cases where it won't work very well. We're not saying that it's production ready, but that's where we hand over to Eric. Any more questions?
Doesn't seem like it. I guess it'll come up later. Cool. Then Eric, if you want, you can start sharing your screen. Thanks a lot, Martin. That was very comprehensive, and you explained things really well, so that helps. So anytime you want to start, Eric, you go ahead. You can also give a short introduction to yourself if you want.
Yes, sure. Can you see my screen now?
Yeah, we can see your screen. It's the website, right?
No.
Okay.
Can you see it?
It's a link. Yeah, it's the presentation within.
Okay.
Yeah.
So yes, thanks. Thanks, Martin. Very complete presentation, and I think there is a couple of things I will repeat during this presentation, of course. So let's start with a few words on who we are at Horizon and where we come from. So I am Eric Benaim, CTO and co-founder of Horizon. I founded the company in 2015 with my partner Pierre Guillou, who, by the way, finished his acoustic study at DTU. So again, Pedro, it's a real pleasure for us to be invited today for this Danish Sound Cluster event. So we started in 2015 with a kind of a simple idea, I would say. We wanted to improve digital active noise cancelling by adding sound scene analysis, digital filtering on top of the INC algorithm. So we have been working for 2.5 years on the first product before releasing it on the market. And actually, to do that at this time, it was really complex. We end up with a awful electronic architecture and faced a lot of hardware constraints because we used 3 different chipsets to do all the filtering. And yes, so for the past 5 years now, we have been mainly working on improving and implementing audio algorithm for Rebel, and most important, and I think that's why we are here today. We have been always looking and testing new hardware architecture, which would facilitate the development and support more and more efficient algorithm. So yes, today our company has two main activities. First, we design and sell premium headsets manufactured in France, like this one for the professional office market. And second, we provide our technology in consumer brand product, focusing on acoustic design, signal processing, and embedded AI algorithm. So our expectation about the audio market, I think I've seen the list of the attendees today, so I think almost everyone here are aware of the impressive growth of the hearable market, especially for two wireless stereo earbuds. So we expect that this trend will continue in the following years, and what I think is that the arrival of GAP9 like DSP platform is key for that, because it allows us, as Martin said many times, it allows us to have time domain, frequency domain processing, and AI algorithm running together on the same platform. So what I wanted to show today with this presentation is to give an overview of some audio technology we are working on at Orasam, and how those technology benefit from this kind of platform. So the best way to do this is to show maybe the evolution of those technology, and give my insight of what we can expect in the future. So I will focus on 3 audio applications. First, active noise cancelling, then transparency. I know Martin already talked about this, and also what's very important for mobile telephony, the voice communication. So yeah, before to do that, the first question we need to answer when it comes to deploying complex algorithm in product is why we think we need to work on the edge, because we can do this in the cloud or on connected device like the laptop or the mobile phone. And of course, running machine learning task on the end device is clearly the hardest task to do. Because yes, Martin already said that, but we are limited in terms of resources, meaning in time and space complexity for our algorithm. And we have also strong constraint with efficiency and battery consumption. But sorry, but on the other hand, if we succeed in doing that, we get a lot of benefits. So we have direct access to all embedded sensor, microphone, bone sensors, accelerometers, then we can achieve very low latency processing, and which is a key point for most audio application, noise cancellation, audio enhancement, voice capture, etc. So also what I wanted to note is what we learn from our customer is that they like plug and play devices to be completely independent from any mobile computer application. And finally, but this is more and more obvious, there is the concern of privacy, especially when it comes dealing with the personal voice pickup signal. So let's see the evolution of some audio application, and let's start with active noise cancelling. So the idea here is to see what's the difference between what we have historically, the static ANC, then adaptive ANC, and now the true adaptive ANC. So I don't know if anyone is familiar with ANC, but let's make it short. The performance of active noise cancelling algorithm for headphones or for earbuds is related to the DSP latency. It must be very low because we need to generate destructive interference, which depend on the sound stimulus. And to minimize the input-output latency. We use DSP with a very high sampling rate, and we process sample by sample. So this lead to high CPU load, and that's why ANC algorithm historically needs to be very simple and efficient. And that's why even today, the structure of ANC is mainly two set of big cascade. One with the input of the feedback microphone and the other one with the feed forward. So like this, with this simple topology, it's possible to shape the required frequency response over the full spectrum with a very few number of biquads. And yes, that's simple, but of course it's it comes with great limitation. So most obvious limitation is that with this kind of fixed filters, you cannot perform well on all tip and kind of noises. And the second drawback is that even small variation of the acoustic of the headphone can have a significant impact on the performance. And this variation can come from many ways, like tolerance of the acoustic component, the mechanical assembly itself, or even acoustic leakage, for example. That's very interesting. That when the user has bad fit with the headphones, because you wear glasses, for example, like me. So there is many limitation, and what we have seen in the past years, there is the first evolution of the ANC algorithm is adaptive ANC. So the idea basically is to store on the DSP several banks of filters, and depending on the background noise or depending on the level of leakage we can measure, we simply have to switch from one bank to another. So of course, this switch can be pretty easily automatic with kind of a simple detection model, but is not ideal at all because every background noise is different, and there is specific harmonic content in that, and every user leak profile is different. So it's not possible at all to have a lot of predefined filter bank in the DSP. So for that, we need a noise control adaptive topology, truly adaptive, to be able to change the filter shape continuously. And that's what we can do now with the CAP9. It's one of the few platforms I think we can do that today, because we are able to combine static biquad filtering and adaptive FIR filtering with a large number of coefficients at a very high sampling rate. So adaptation is done in parallel, and we can achieve great performance and have a real personal adapter for the user. So yes, let's switch with another application, hearing enhancement, and at the beginning of this, it was the transparency mode. So transparency mode, the ambient sound is captured by an external microphone and is mixed into the music stream. So it allows the user to be able to be aware of the surroundings, even when he's using closed headphones or when he's listening to loud music. And so at the beginning, static transparency do that, and the implementation use the same topology as for static ANC with low latency, but then it suffers with the same drawback. So the processing is omnidirectional, so there is no real adaptation to the sound environment. And what we can find is just adding some limiters that can protect the user by clipping the level of noise that would be returned. So that was the first step. And in the past few years, what we have done at Rosen, we have developed what we call the Aware Plus technology that try to make transparency algorithm better adapt to the context. And with this, we are able to suppress the background noise while passing through kind of important sound event like alarms or speech when the user is having a conversation. And to do that, we combine ANC processing with beamforming techniques, source localization, speech enhancement algorithm. And when you can do that, it's a totally open door to like hearing aids application, even if there is still a lot of work to do because hearing aids application needs a lot of optimization. But what I think is that if we to have a large adoption of this kind of technology of adaptive transparency application, actually we need to have three things combined. The first is that all the process parameters should be completely hidden to the user. You don't want to have any app control. You want to have automatic tuning, in fact. And the second is that we want to have a process that preserves the naturalness of the signal, especially for voice. And the third point is that we need to keep the latency of the process very low. So that's a very complex task. And especially for hearing aids, I just said, for example, when you have a 40 millisecond processing latency on audio, it can meet a lot of demand application. But for hearing aids, 40 milliseconds is too large to deliver a good listening experience. So in that way, we have a lot of work to do to compress this latency and to enhance the user experience. So the third application I wanted to talk about is noise reduction application, especially for mobile telephony. So if we step back a bit, this kind of noise reduction task is usually performed by audio processing based on statistical model. And mainly it consists of a spectral estimation of the noise with a voice activity detector. And first, the noise is estimated on speechless segments, and then the noise is removed in order to keep only the voice of the user. So that's the basic idea of noise reduction. And that's what we have been using for the past 20 years, actually. And those techniques works well for stationary noise, when you are in the airplane, for example, but they are not good at all for non-stationary noise when people are talking next to you or when there is the music in the background. And those techniques, they are definitely not good in a very low SNR situation. So the hard part of denoising is to make it work well, but all the time and for all kind of noise. And I mean, we have been working on this for a long time, and there is always some noise that will cause problems and that require more and more tunings. And that's why we now use deep neural network to capture deep information of the audio content, because we are able to better distinguish between noise and voice. And of course, it results with the gain of performance. So yes, this deep neural network have a very high separation capability, but it comes with a price, very heavy computational costs. So it requires more memory and more CPU usage at the inference time than every other algorithm. So saying that, now with a Gap9 chipset, we were able to run speech enhancement model with 1.5 million parameter in real time. So we will see that in the next slide. I will show you a concrete example. So, so to conclude with the evolution of voice communication algorithm, There is another step we're working on. We can say that it's personalized processing. I think it's the main trend in the research field, and work is in progress at Horizon on that. We work on voice embeddings techniques. This is a kind of a discriminative representation of the speaker voice. And this tend to enhance, again, the ability of the network to better separate speech and noise. And it shows significantly less distortion after processing the user voice. So, yes, this is the example I wanted to show. So this is the diagram of AI-based denoising process. It's working on GAP9, and as usual, speech enhancement is done in the short-term Fourier transform domain, and typically use 32 millisecond window. So larger window contains more sample, and the frequency resolution can be higher for potential better enhancement. So in this example, we use 16 milliseconds to reduce 16 milliseconds of window overlap to reduce the CPU load and to reduce the power consumption. So the innovation here with the GAP9 architecture is that we are able to mix noise reduction, echo cancellation, cluster processing with high load neural networks for only 15 milliamp per hour of power consumption. So that's terrific. I say I've never seen such performance on other chipsets, because the model is big. It's 1.5 million parameter, but as Martin described, GAP9 offers a large storage capacity. And as I said before, now this kind of model better discriminate the user voice, even in low SNR environments. So let me try to run this example. So I have attached an extract of processing. This extract is a pretty challenging, because the SNR fluctuates between -10 dB and -5 dB, and the background noise is a recording of open plane offices.
When the birds could find very little to drink, a thirsty crow found the pitcher with a little water in it, but the pitcher was high.
So that was the reference, and the microphone closer to the mouse. And this is the processing.
When the birds could find very little to drink, a thirsty crow found the pitcher with a little water in it, but the pitcher was high and had a narrow neck.
Okay, so yes, so that's the result of the processing. It's running in real time. It's less than 40 milliseconds of total latency, and it's outperform of course classical statistical denoiser, but also recent RNN architecture, like you probably heard of the RNN noise architecture, which is very lightweight, but it outperform this model as well. So I'm almost finished. To conclude this presentation, let me just point out that from my perspective, all the elements are in place to drive industry adoption of this kind of DSP and parallel DSP. Because first, it's the first time we can run such type of algorithm on the edge with a very low power consumption. So that was actually the high computation capability that we were looking for, improved audio use cases. And second point that is almost as important as the first one is that this platform is flexible, and you have seen it comes with great tools. So it's not easy, but we are able to deliver hardware and software solution with rather fast cycle of development. And I think that's mandatory to have a large adoption of such tool. Thanks, everyone. I'm open to question.
Thank you, Eric. There's no questions yet. We can wait a little bit. Maybe you can take out your share screen. But meanwhile, maybe I have some questions. All right, so I'll start with Martin. You mentioned something about the development experience, and that's actually one of, so I also make hardware, and that's one of the main focuses we had as a headphone developer, to make sure that we don't spend way too much time trying to figure out how to make things work. And as such, that had a huge impact in the DSP platform that I chose back then. So the one you have right now for GAP9, can you explain that in simple terms? So you have a compiler, and then you can program in C, and then is that easy, or how do you just explain that a little bit? Or can I, like, if I'm an academic, can I go through MATLAB somehow and then figure it out from there?
Yeah, I think, I mean, there's multiple levels to making things easy from a development perspective. I mean, an example is worth 1,000 words, I think is kind of like true in software development. It's always, I think, also in software development, what's true is if you've already done it, it's much easier. So examples are hugely important, and we include a huge amount of examples. But yeah, the fundamental development process from, and there's kind of 3 different disciplines that we've got here. There's one which is an embedded developer, there's one which is an audio designer, and there's one with the neural network guys. So the neural network guys actually very often are coming from a cloud environment, where there's kind of endless resources and massive GPUs and stuff like that. So they tend to not be very aware of optimization problems. So what we try and do is give them a path from TensorFlow through this TF Lite, which kind of starts to constrain them a little bit, and then have a series of tools that, as much as we can do, kind of reduces the complexity of the network as it's passing through those tools. So there are some constraints that we put on. For example, if you're developing a TensorFlow, your graph can change. Kind of your graph can be dynamic, so the sizes of things can be dynamic. Well, we say no, you have to fix them. So at a certain point, you have to fix those dimensions. So we kind of try and make that process sort of by stage. We also try and make each tool fairly modular. Most of the people working for the company come from kind of more a Linux sort of background, and we like small tools that do a fixed function that we know what it is, and we can see the input and we can see the output. Because then if one of them breaks, it's much easier to fix stuff. If there's a kind of magic box and you press a button and the right stuff is supposed to come out the other side, but when it doesn't, you're really in trouble because you have no idea about what's going on inside. So all of the tools are kind of in that essence. The embedded guy, well, we're GCC, we're bin utils, it's cross-compiling, it's kind of very, very classic. The build system, we're just moving to a full CMake build system. It's very, very classic, but you could build it however you wanted to build it. But again, it's fairly understandable. And then from an audio perspective, we kind of have a hybrid approach, because one of the things we're integrating is the ability to have a kind of runtime platform that can handle all of these different audio filters running across these different pieces of hardware, because we could have bits of an audio graph that are running on the SFU, on the FC, and in the cluster. And bits of that audio graph can be a neural network, could be a normal classic filter, and you've got all of the, the buffering and timing and time zone kind of stuff, clock domain stuff to manage in that. So we have essentially a graph description language that we have a visual front end for. That is kind of a two-stage graph description language. So with a kind of component idea. So you take a component, a kind of template for a component, and then you make an instance of that component, and those components can be filters which can be executed in the SFU or anywhere actually in the platform, but it also could be codecs, can be neural networks, and then you assemble those together, and the runtime compiler kind of figures out what is the scheduling across that graph, and then produces the code in C for that. And again, what we like to do is produce C, because then you can debug it. Because then the embedded program can say, okay, well, this isn't working. We don't produce, .bin type things. In some cases, for the configurable things like the SFU, there we produce a kind of description of the graph that's going to run on the SFU, and we have an SFU compiler product which actually produces headers. But those headers are essentially just sets of configuration for their C headers, and you can use those directly with the API. And they're essentially sets of configuration for those things.
And Martin, you said that there is a lot of tools for optimization of the AI models, and I think one of the thing we can share today is that you said it. A lot of people are coming from the academic or from the cloud industry, so they are used to work with big models, and that's not obvious for everyone. That's not, I think, the right way to do, to take a big model and try to fit it into
absolutely
the you have to sync your model and your learning and your feature depending on your use case and the product you want to embed this. So that's another kind of thought.
Yeah, I think that's true, but I think it's also true that if you don't have a big model, then you have even more problems. I mean, I think the first thing is actually to have something working properly. If you had something working properly, that's already a step forward. Then, yeah, okay, definitely agree with you that the next step is getting it down to a size which can run in something like that. And it's true that, I mean, there are huge models that will not run on GAP, or even if they can run on GAP, and some of them will run on GAP, will run with perhaps GAP 100% concerned with that model. And when I'm talking about models like that, I'm talking about models with tens of megabytes of parameters, and but there is an awful lot of work being done more and more inside the machine learning community to optimize these models in various different ways in terms of things like automatic module tuning. There's lots of compression techniques which are being used now, which definitely are kind of making their way up into the training space, which I think is really where they need to be. So you start to constrain the model while you're training it, and you're kind of stripping stuff out of it while you're training it, so it learns to cope with this reduced amount of parameters. So I think there's a lot of things going on which allows us to get some of these models down to size, but mostly we find that customers have the most problems are ones that don't really understand the problem they're trying to solve actually at the beginning. That's very often a problem.
Yeah, I think we have a question here. Could the GAP9 be used for amplifiers like ICE power or similar components, even though it's focused on wearable electronics?
Yeah, I mean, GAP9 is applicable where you want to do intensive computing on images or sounds inside something that's very, very energy constrained. So that, and that can be in lots of places. But the energy constraint is really important. If you can use if your application means that you can use, a quad A53 with some huge, neural network processing accelerator, and you don't mind if it consumes hundreds of milliwatts or even watts, then okay, it's not the right product.
Yeah.
So no point.
It makes sense for a low power device.
It makes sense for a device where power is a concern, and that can be in devices where there's a standby mode, for example, where you don't want to, we're all very sensitive now to the amount of energy that we're consuming when things are in standby, and a lot of people switch them off. Well, if you want them to keep them on, then start thinking about making it consume microwatts instead of watts. I think the European, I remember looking at the European standard on standby, and it was, for me, very, very high. It was kind of like watts. Well, it wasn't even milliwatts. I think there is one standard where it's milliwatts, but it's hundreds of milliwatts. Well, that's still, that's a lot of power.
That's a lot. All right, cool. So what about okay, so clearly one of the main advantages here is that you can do machine learning and DSP and all that stuff in one place. And Eric, you even mentioned that in your previous product, you have 3 cores or 3 different chips, and that's a pain, especially for the firmware person. But so that seems to be one of the core, beyond DSP statements of this. But let's say I'm not ready to use AI yet, and I want to focus solely in the DSP part for now. Is it still an advantage? Is it still a better solution than the more known ones that people just like the Hi-Fi 5 or whatever, if I don't want to do any machine learning, for example?
Yeah, yes, actually there is, in the presentation, I talk about 3 applications, and the ANC application, as I presented it, doesn't involve any AI. There is some expectation to use AI to drive the ANC, but adaptive ANC that allow to have leakage compensation for every user and adapt to their environment. They use only the DSP, and the advantage of the GAP9 is it can combine backward and adaptive FIR filtering. So that's pretty new to do that with low consumption and low latency. And especially for FIR, because I work with other platform, and the number of coefficient with the GAP9 can go up to 256 coefficient, and have a very low latency. So that's remarkable.
And if I understand correctly, so some of those functions, DSP functions, some of them will be in the DFU and some of them will be in the cores, and that's why it's so powerful, even just for DSP.
Yes,
right.
It is, and what we have in other chipsets, the static big-wide structure, it's not good at all for adaptive algorithm, true adaptive algorithm, because optimizing coefficient for big wide cascade is like a non-convex optimization problem, and that's not possible to do this on this kind of DSP. So you need to work with FIR filters.
Yeah, the cluster, it can also be used for general purpose DSP, so it can be used for things like codecs and FFTs and frequency-based filtering and all of these things. Anything which can be expressed as either a stream-based or divide and conquer kind of parallel problem can be solved by the and really things which are really quite difficult to parallelize can be expressed in that way. And it's very much a kind of hard. If you program something in kind of OpenMP or something like that, then you kind of understand how it works. It's really a kind of fork and join, synchronization primitives, parallel fors, things like that. In fact, we have support for an OpenMP, a reduced form of OpenMP library.
Great. All right, I think I have a few more here since we don't have any more rolling. We have a few more minutes. So you mentioned AI. Especially you, Eric, you mentioned AI in the hearing enhancement part. Yeah, as you know, that's being done already by the hearing companies. I'm not so sure a lot of people are doing it yet. But how do you plan to do that? Because, you know, for many years, we've just been doing the regular DSP for the hearing side. So what's your vision on using it with this architecture also? If you've done something, or I don't know how confidential it is, but just give us some lights about what this...
Yeah. I can give maybe 2 ways to find more performance in this kind of product. The first one is that actually there is 3. Now people don't like to wear like hearing aids at a young age, so that's the first problem. But I cannot solve this one. Is not a kind of performance issue. It's just a society problem. And what I've seen is that earbuds and true wireless and the hearing aids product, there is kind of a convergence between these 2 worlds. But so this first issue will probably be solved by the time, just with time and mentality change. The second one is a performance, I would say, because it's really hard to find a good product. And as you can see, it's when you do ANC, you reduce the background noise. When you do speech enhancement, you enhance what's useful in your ambient environment. So yes, it makes sense to combine those things and to think we can have better hearing with that. But still now, as I said, it consumes a lot of CPU, and the latency, as I see on my side, is a bit less than 40 milliseconds. So from my point of view, it's not enough to have a very good experience for all day long with the hearing aids. So that's one of the problems we are tackling right now. I hope we have some news in the future. And the third one is a bit more complex, but it can involve also intelligence, artificial intelligence. It's the tuning. Tuning of this kind of product is very complex. You need to try several parameters, and often when you do this tuning, you are not in the situation you are living. You are at the doctor or some place to do the measurement, and I think that's a big mistake, and AI can help with that, to do automatic tuning and to have reinforcement learning to adapt this product. Yeah.
Do you have anything to add, Martin, about that?
I think Eric really covered the topic. I think there's I think that the tuning aspect is the one which is particularly interesting, I think, and some of the things which are happening from an AI perspective in terms of on-device training. I mean, Eric mentioned reinforcement learning, but there are some interesting things happening in on-device training for kind of regression and classification, mostly for classification kind of tasks.
Sure.
But if there's a way to get a feedback loop from the customer, so from the person who's wearing the thing, so that they say, you know, at this moment with this noise environment, I am having this problem. That can be used from an on-device training perspective to you know, reorganize the device and to learn over time what is comfortable for the person. And that's perhaps better than the person having to go to a clinic and try and explain, and then have a fitting session that's very, very long. So
the word comfort is very important, because until now we have always been working minimizing some optimization problem, minimizing some energy, but with adaptive filtering and AI, we can think of optimizing noise comfort, yes, and have the feedback from the user and to find other kind of optimization than the standard one. Yeah.
So I mean, you're not thinking about like the classical hearing algorithms as well? Would you combine it with those, like the rationales and the usual crime you know, the beamformers and the noise suppressions, and would you then combine these with this approach of removing unwanted noises with AI and amplifying?
Yes, of course. I mean,
Yeah.
it's a chain of processing. Of course, you
Right.
can think optimizing each block independently, but at the end of
Right.
the day, you need to have a full system. So of course, if you have a way to measure the comfort of the user, of if the evolution of the hearing, depending on the situation and depending on the real sound if is faced every day, then you can adapt to the hearing to compensate the hearing loss, but also adapt on the type of noise he's facing every day.
Guys, that's great. I mean, we only have a few minutes left, so if you have any things you want to say, like besides all this we talked, any last remarks?
Right, I'd like to say thank you for inviting us. I think it was it's a really interesting, for us, it's really interesting to have this kind of, look from both sides, cross-pollination between the people who use the hardware and the, and we're always very, very interested in getting this kind of feedback from the people who are using our hardware to kind of optimize it and to change the tools and so on. Obviously, when you build hardware, you build a lot of software. Probably more people working on software than hardware. So we're always working on our tools to make them better for these kind of tasks.
Awesome.
Yeah. Anyway, thank you very much.
Thanks a lot, Pablo. Pedro, sorry.
It's all right.
And
a lot of people get that confused.
Yes, now it has been maybe 1 year. We have been working with you, Martin. And yes, maybe the last word is that again, things are changing, and I think there is more to come. Yeah, with this kind of platform.
Awesome. And I hope to see you guys here in the Danish Sound Day. But it's in just a few weeks. So, but then I'll just mention also, thanks a lot, guys, for accepting this and for providing this knowledge to the community. I think this is what it's about. I just want to mention that next week we will have this part 2 beyond DSP. It's also going to be very interesting and very different from this one. But if people want to watch it, then they can just go to our website and check out the event. And lastly, we have a survey after. So when you close this, there will be like a very short survey, just so we get as much feedback as possible, so we can improve what we're doing here. So if you can take a minute, just fill out the survey. And I think that's it. So thanks a lot, guys. I am going to stop the recording.